Next semester I want like only afternoon classes. Like I don't care if I have to like be in class until like 6 as long as it starts like I'm just tired.
Okay, I like what is it called? What's this
Almost safe to double here.
But it wasn't a fundamental error to where like I don't understand physics. It was like I literally just like misread or like my brain not only misread it, it's like okay, you know how the one on the pole like the thing was like going that way but like no. Which direction tension pole?
Yeah, I haven't done that before. What if you just got a heart rate?
Can you get a heart rate?
Certainly.
I feel where's Sarah?
Hey, good morning, everyone. I realized a couple of weeks ago I promised I'd continue to use this and then forgot to do so. So we can just get this at the right application level. Okay. See how this works. Okay, so reminder, today is 1 week since the first midterm was returned, so you have a week if you wanted to submit a regrade request to do so, so today is the deadline. Don't forget about that. So we're going to continue our exploration of momentum conservation and wrap it up for today. Talk very briefly about momentum conservation in one dimension, a little bit more about momentum conservation in 2D, where the calculations inevitably become a little bit more involved. Might do a worked example, hopefully we'll have time for that. And then I want to spend a little bit of time talking about two specific subtopics as we address the idea of linear momentum. The first will be to examine what's typically called rocket motion, reasonably obvious description of what it will be describing. Just a heads up, if you think about rockets, the way rockets work is they're typically carrying a large amount of fuel, which is getting burned in some way and expelled as the rocket is firing. So of course, what we are confronted with in the case of a rocket is a system in which the mass is continually changing, okay? So that's obviously different than the scenarios we've looked at so far, where the mass is constant. And so looking at a mass-changing system in terms of momentum conservation is going to be useful and will help us learn a little bit about how to design efficient rockets. And then we will turn our attention to the concept of center of mass of objects. And this is really the first time we start to break away from our idealization up till now, which is that most of the objects we've been dealing with are in fact extended. We've kind of treated them as point-like objects. So we're starting to move away from that. That has implications both in the context of momentum conservation, which is of course why we introduce it here, but it also has a lot of relevance as we turn to our next new topic, which we may get to today, but if not, certainly on Thursday, which is starting to look at rotational motions, okay? So that's the roadmap for this morning. Okay, so let's see, a bunch of things up on the bench up front. I guess I'm just going to start out with one of them as a quick reminder of one-dimensional momentum conservation. And it's this gadget here, which many of you have seen some variant of before, typically in the form of a kind of executive office toy. It has the name of the Newton's Cradle. And so what is it? Well, it's 5 hopefully equal steel balls suspended from strings, so they're all in a line. And it is a nice demonstration with a slight subtlety, which I'm going to try and show to you, about momentum conservation and pretty much elastic collisions, not exactly, but close to. And so you know roughly how this thing works. Your board executive, she takes one of the balls on her Newton's cradle and pulls it aside and lets it go. I've forgotten what easy please crowd you are. All right, so obviously the motion has subsided, but initially what you see, and I'm talking about this being essentially one-dimensional, that's a little bit of an approximation and there are other things going on here. But as I raise this thing up and let it go, first off, you now have tools to figure out what's going on with the motion as this thing falls. Possibly energy conservation would be an easy way to analyze that. It's not the only way. You can analyze it with forces, Newton's laws, but energy conservation would be a good way to do it. What's happening is as I raise this thing up, it's gaining increased gravitational potential energy. I let it go. That increased gravitational potential energy gets converted, if you will, or exchanged to kinetic energy. So by the time this thing is down here, it has some speed, obviously. It has a certain mass, has a certain speed. And it's about to hit this thing in roughly a horizontal straight line, okay? So we know its mass, let's say. We know its velocity from energy conservation. It's hitting this, and then it's hitting a neighbor, which is essentially an identical steel ball suspended. It's pretty much collisional in nature. Turns out it's pretty much an elastic collision. So momentum conservation, let's say the first order kinetic energy conservation. If I simply did this with 2 of these, you'd expect that this thing bounces off and bounces up more or less in the same height in the other direction. And that would indeed happen. I'm not going to show it, but what we have now is not 2, but 5 of these things. So each of these things undergoes a collision. It immediately more or less collides with its neighbor, collides with its neighbor, collides with its neighbor. Once it gets to the last collision, there's nothing left for it to collide with, so it's going to start moving off and it's going to essentially do the inverse motion of this thing as it came down, okay? So that's what's going on. Lots of kind of nice energy and momentum conservation stuff going on here. And as you saw, it doesn't last forever. Eventually the motion dissipates, tells us it's not perfectly elastic collision. Some of the energy is being lost. You can even hear where some of the energy is going. Probably there's some heating effect here as these things collide with each other. So it's a nice simple demonstration of a lot of stuff we've been looking at for the past week or so. What I was tempted to try, and I haven't actually done this, I just found an elastic band up in my office. It's going to be hard to get this to stay in a line. Maybe even impossible. What I wanted to do was try and show you what happens when I block the 4 of them together. But the elastic is maybe going to make this go. Okay, not so bad. All right. Okay, it's not going to behave for very long. Maybe I'll try one more time. This would effectively make this, instead of 5 equal masses that are undergoing elastic collisions, it would make it a 1-to-4 mass ratio and a simple collision, if I could make it happen before this thing goes off axis, and as soon as it does, it's going to go crazy. So this is a really bad idea, but let's see. Okay, what you saw is that the whole assembly of 4 things moves much less. Okay, so that's a reflection of momentum conservation with a 1-to-4 mass ratio. All right, so it doesn't stay in line, but you get the idea, hopefully. Okay, so that was a quick demonstration of one-dimensional momentum conservation. We talked at the end of Thursday's class about two and potentially three-dimensional momentum conservation. And I just wanted to say a little bit more about some of that. Won't be too involved, but I think I might actually go through a worked example because we did not do that on Thursday. And I know you've been kind of asking for a little bit more of that in class. So, quick recap. Let me call this 2D momentum conservation. Okay, so P final equals P initial, so long as we have no external forces acting on our system, however we've chosen to define it. Since we're working in 2D, we're going to apply momentum conservation in two perpendicular coordinates, often x and y, Cartesian system. So we might say that this is going to tell us that Px final equals Px initial, and Py final equals Py initial. So that's momentum conservation, two perpendicular directions. Only thing I reminded you at the end of Thursday was to be careful about signs. That's important. Probably the example I'll do will illustrate the relevance of that. And if we have an elastic collision, remember the definition, which is that kinetic energy is conserved. And so if it's elastic, you would also have a K final equals K initial. Again, only in the case it's an elastic collision. So, vectors and a scalar. And those in principle will give us three equations to work with, okay, if we've got an elastic collision. Now, we determined at the end of last time, I don't think I'm going to write this up again, it's a little bit too involved, but this is again for elastic. What we saw from last time, and again I'm not going to do the algebra here, so hopefully you can look back in your notes, was applying all of this, we saw that the following was true. And again, this was an elastic collision, and my recollection is we were looking at the case with a stationary target. This result happened to drop out, okay? So nothing particularly remarkable about it, but it's in fact a specific case of a somewhat more general expression that I'm going to write up there. We're not going to prove it. In fact, I'm not going to ask you in general to make use of it, because typically I'll be asking you to solve the problem from the beginning. But I just want to mention it because it's kind of useful thing to know. So this is a specific case or example of a more general result for elastic collisions, which is the following. Okay, so here we go. Unfortunately, this is right at the top of at the bottom of the chalkboard, but hopefully you can see it. All right, let me just remind you of the notation. Obviously, we're talking about velocities here, and this is talking about the velocity of object B afterwards. I should have been maybe consistent with initial and final versus 1 and 2, but I know in the example I did last time it was 1 and 2. So it tells us that the velocity of object B after whatever collision we're talking about minus the velocity of object A after the collision is equal to the negative of the difference of the velocities before the collision. Okay? So again, it doesn't look particularly illuminating perhaps, and it's not maybe entirely clear where it's come from, but let me just tell you what the general result is telling us for elastic collision. So in words, for elastic collisions, the relative velocity of two objects before and after is the same. And I ought to be a little bit more careful with my wording here. It's actually the magnitude. So this becomes a kind of a mouthful. But you can see that that's what this expression down here is representing. And this turns out to be true for all elastic collisions, okay? So the relative velocity of these two things is preserved, if you will. There's a sign change here, but that's what we're going to find is true for all elastic collisions. So again, I'm not going to ask you to use that or remember it in general. More likely, I'm going to give you a problem to kind of work from scratch. But it might be useful just having this in the back of your mind, maybe as a question once you've done a calculation to figure out, well, is it actually true that the magnitude and the relative velocity is preserved in any elastic collision? Okay? Good. All right. So let us then maybe do I'm going to work through one example, maybe with your help, just because we were a little bit hasty last time. So, two pool balls striking off center, and I'll try and demonstrate this for you in a moment. And so here's my sketch of words. I'm not going to write the words up, it's not a good use of our time. But let me try and schematically represent what's going on here as quickly as I can. So I'm going to start off with one object B at rest. I'm going to start an object A coming along here with a certain initial velocity. Let's call it VA1. Initially at rest, and then I'm drawing both before and after simultaneously. We had a sketch like this at the end of Thursday's class. So object B is heading off in this direction as a final velocity VB2. Object A down here as a final velocity VA2. I've already superimposed a coordinate system on here. Let me add some angle definitions. This will be a very typical setup. And, okay, so let me tell you that we have the mass of A is 6 kilograms. The mass of B is 3.8 kilograms. Let's see, we've got the velocity of A before the collision is 6 meters per second. And what else do we need? Yeah? Okay, that was not smart. I realize I've been drawing the diagram for another question. Okay, bear with me. Let's see, I am going to switch this over to this problem. All right, so just bear with me while I correct my screw up on this. I realize I was writing the wrong numbers down. So this is 5 kilos, this is 3 kilos, and this is 4 meters per second. Okay, now we're back on track. And I'm going to claim that this is an elastic collision. Okay, so I'm going to demonstrate this in just a moment with the Airtable, and then I'll give you a brief intro to this problem. Maybe I'll ask you to work it a little bit, and then we'll talk through it. Okay, so a couple of you talked to me after the end of class on Thursday about what is it that makes these things move off other than in a straight line, and of course the answer is when these things collide in a way that's not head-on. So if they collide in a way that there's a translational or sideways offset between the two objects, then there's going to be impulses given in such a way that they move off in certain directions. So let's see if I can show you this quickly. Okay, 2D analog of the air track, now an air table, same idea, lots of pinholes with air blowing up. Roughly speaking, makes this a friction-free horizontal surface. So let's see if I can represent this from your perspective. Okay, stationary target, incoming puck, moving with a certain initial velocity. I'm going to try and make this thing hit head-on, which is probably not going to work so well, but let's see what happens. Okay, roughly. You can tell it's a far from perfect air table because you saw that that thing didn't move in a straight line. But let's try now with a slightly larger momentum, slightly larger impulse. And I'm going this time to try and make this thing hit so that it's not hitting head-on, but it's hitting with an offset. Okay, I'm going to make a really good head-on version. Let's try again with more of an offset. And one more time. Okay, so that's the situation we're looking at. I'm going to claim this is close to an elastic collision. These things back in the day used to have kind of elastic bumpers on them. That's not so much the case anymore. But we've got an elastic collision here. Okay, so let's see what we've got and let's see if we can make any progress on this problem as it stands. So, what do we know? Momentum conservation, and if I'm claiming it's an elastic collision, we have kinetic energy conservation. Presumably I'm going to be asked to predict or determine something about the motion after the collision. So the thing I want you to think about is how many pieces of information do we have, how many are we missing, and how many equations do we have as tools to figure out the missing quantities. So what do we need to think about? We know when we're talking about conservation of momentum and energy, we're dealing with masses and velocities. So what do we know? We know masses, that's fine. We're told some initial velocity here. Fine. That's all the stuff we know before the collision. We know everything before the collision. What do we know afterwards? Well, so far the masses are unchanged, so those are fixed. But now we have two velocities and two angles on that sketch. So I know all the variables as I come into this collision. But in terms of after the collision, I don't know either velocities for the two objects or angles. I have, well, you can tell me, how many equations do I have for momentum conservation applied to this problem? 2, right? So I'm going to apply it in 2 perpendicular directions, presumably the way this is set up in x and y. And I've told you it's an elastic collision. How many equations do I have from energy conservation, kinetic energy conservation?
2.
1. So, total 3 equations to work with at 4 unknowns. Okay, so clearly this isn't going to work, and of course you're going to need more information to be able to solve a problem like this. So, we need at least one other piece of information. And so in this problem, The additional piece of information that we are given is that the velocity of object A after the collision is 2 meters per second in some unknown direction. Okay? But now we have our requisite additional piece of information. I am going to ask you just to take 2 or 3 minutes and just work on this with your neighbor. Okay? Again, fairly straightforward, but I want to make sure you're well practiced with this. So take a couple of minutes, find a neighbor, talk how you're going to solve the rest of this problem, and then we'll just quickly go through it on the chalkboard. Yeah. All of the remaining things that we don't know. So the question was, what are we solving for? So I want you to know I want you to tell me the velocity of object B after the collision, and I want you to tell me the 2 angles. Okay? Okay, go for it.
I woke up at like 9:30. Feel 70% of the income. That's an extra.
And then the extraction of the velocity of A is like cosine theta, like cosine theta A. Yeah. We just assume that's like
I know if the angle would be that.
yeah, I can't go straight on because then it'd be a head-on collision.
I think we're in the past.
Wait, so would we include it? Oh,
Yeah, we need those. Like it says, so it's gonna take a long time.
Wait, we know that kinetic energy or whatever is conserved. Well, oh, kinetic energy is conserved for both directions. Or just one direction. We don't have to think.
no, we have to think like X and Y.
This should be this first one. That's like that's not right. Because then momentum is in the x and y, right? Momentum is mass x.
So I'm hoping you'll find this a relatively short problem. I'll give you another minute, and then we'll just quickly talk through, make sure you've got it, and quickly wrap up the calculation.
And then we also know in the y direction.